Hello friends, in this video I shall be touching upon the basics of geometrical optics. It's an aspect of physics which deals with objects and how images are formed out of it. So how can images be formed? By a process called reflection, or by a process called refraction, or by diffraction and other processes. Now reflection takes place from mirrors. Refraction happens from lenses and other mediums such as a bowl of water, but I'm not going to discuss about refraction in this particular video, but definitely in the subsequent video. So let me focus upon reflection from mirrors. But before I move forward, let me say that what is an object and what is an image. The definition is a very fundamental aspect that needs to be clarified. So if I have something which I call an object, in that case it must be emitting rays, or rays of light must either diverge or appear to diverge from that point. If they actually diverge from this, it is called a real object, and if they appear to diverge from this point, it will call a virtual object. Now I'm not going to talk about further detail right now because it will become clear later on. Similarly, if I call something as the image, then rays of light must meet at that point, either actually or virtually. Depending on that, it's a real image or a virtual image. Now I'll discuss more about these things subsequently. Okay, so let me start with mirrors. Mirrors are of three types mainly: plane mirror, convex mirror, and concave mirror. So a plane mirror is what it sounds like, just a plain mirror, and one side of it is silvered, the other side is free to receive radiation. Now I'll also draw another horizontal line like this. This line is known as principal axis. It's somewhat like the x-axis in a graph, and the beauty of a plane mirror is that whatever object I keep at whatever distance from the mirror, it will have an incident ray and it will get reflected back at the same angle. So the angle of incidence and the angle of reflection will be the same, and let this object be there, O. It has innumerable points, but I'm only going to consider the topmost point for convenience. So when it hits it normally, it will get reflected back normally, and I can take any other ray like this and it will get reflected back at the same angle of incidence. Now notice that this and this are diverging rays. So where's the image? So I want image to be a point where the rays either meet or appear to meet. So here I'll have to pull back the lines, and here is the point where the rays appear to meet. So in this way, this virtual image I will be formed, and if I do a little bit of geometry, I'll find that this object distance x and the image distance y are equal to each other. So you have a virtual erect image which is equidistant from the mirror. Fair enough, this concept was aptly cleared. Now I move on to convex mirrors. So a convex mirror is one which is something like this. It's a part of a sphere actually, and the inner side is silvered out, the outer side is ready to accept radiations, and again I will draw something called the principal axis. Alright, and I will mark certain points. First of all, f, the focal length, 2f, similarly here f and 2f. Now a convex mirror is essentially a diverging mirror, and a concave mirror is a converging mirror. What do I mean by this? When rays of light fall upon a concave mirror, they will generally tend to diverge. The divergence power is maximum when the rays of light come from very far away, when the object is very far away. So nearly parallel rays of light are coming in this way. Alright, they will tend to diverge away in the best possible manner, maximum divergence. Again, we find divergence happening, which means that a virtual image will be formed behind the mirror. So I retrace the points back, and the point at which this image is formed is at the focal length, and it is at a single point. Because the divergence was maximum, at the opposite side of the mirror you have a highly diminished image reduced to a single point. So it is a virtual image reduced to a single point. Now this is important. As I move closer to the mirror, say I move here, this image will become here. Then if my object is say at 2f, then the image will come say here. Then if my object is say between 2f and f, image will come here. Then if my object is at f, my image will come here. Then if my object is coming closer, my image will come closer, until my object comes extremely close to the mirror, and the image is also extremely close and nearly equal in height or length. So as you can see that my object has come from infinity right to the mirror. This point is called the pole of the mirror. So it is coming from infinity all along the principal axis right up to the pole, and my image is coming from the focus right up to the pole. So we have a virtual erect image, and the divergence power decreases, and therefore we no longer have a point, we have slightly bigger and bigger images. But we have virtual images which are in general smaller in size than the object. So a diminished virtual erect image is formed. How is it useful? Also, let me consider one more aspect. As the object is coming from infinity to the mirror, the image is coming from f, the focal length, to the mirror. So definitely the image is moving slower compared to the object. Now let me consider the object to be a set of cars, for example. Alright, they are coming closer to the mirror. The image of those cars will be smaller cars which will appear to come closer and closer. So if I keep this convex mirror as a rear view mirror in my own car, then it is of such practical utility, because the big trucks will be coming and my plane mirror won't be able to accommodate that. A convex mirror will shrink the size of this big truck into smaller trucks, and I will be able to see it. Although if the original truck is moving at a huge speed, the image will not appear to move at such a speed, but still the driver will get a habit and understanding as to how the cars are coming from behind, and a huge spectrum of cars will be diminished and covered in an erect image manner. That's why this is very useful in the form of rear view mirrors in cars. Alright, now let me go to the final type of mirror called concave mirror. A concave mirror is very similar to a convex mirror, except that the inner side is the place where the rays of light are actually received, the other side being silvered out. Again, I will draw the principal axis in the very same way. Alright, so now I consider certain points f to f, here also f to f. Alright, now this concave mirror is essentially a diverging mirror, and the divergence will happen the best when the image is furthest. So when the image is very far away, parallel rays of light will appear to come, and this converging piece of mirror, man, it will converge it right to a single point. and that is called the focus. This time the rays of light are actually, and not virtually, they are actually meeting at this focal point. So if you keep a piece of paper, it will burn. All right, so they're actually meeting at this point. So it's a real image, and it's a highly diminished image because it is a converging piece of lens. It's not a lens, a converging piece of mirror. This converging power decreases as the object moves closer. So once again, if my object is somewhere, say here, all right, then my image will be somewhere, say here. When my object is at 2f, the image will also be at 2f and of equal height. When my object is between f and 2f, my image will be far away of a much greater height. So as you can see that as my object is moving closer and closer and closer and closer to the mirror, my image is moving farther from the mirror. It is increasing in its height, and it is inverted. It's becoming bigger and bigger and bigger. Inverted image. All right, till you keep the object at the focus. When you keep the object at the focus, it comes at the break-even point, and it no longer converges as such, but rather forms a parallel beam of light. I'm not making the right type of diagram. So when you keep the object at the focus, then a parallel beam of light is created. You get a parallel beam of light. Now I'm not going to the ray diagram per se. You'll find it here, and if you want, you can refer to these ray diagrams. They are also available in the NCERT book, but what I want to give is an intuitive understanding of what is actually happening. That when you're coming closer and closer to the mirror, the image is becoming larger and larger, inverted and farther away from the mirror, till at a point F they become parallel rays of light. So because they become so strong parallel rays of light, they can be used in torches. All right, they can be used in torches. What happens when the object comes further closer to the mirror between F and the pole? So when it comes here, it ceases to become a converging mirror and instead becomes a diverging mirror. It diverges and creates a diminished, erect virtual image, very similar to a convex mirror. So because it happens only in this range, so it can be used as a shaving mirror, because when you're shaving, you use the shaving mirror very close to your cheeks. So the distance between the mirror and your cheeks will definitely be less than the focal length of the mirror, and it will lie in this region. And because of that, a small but erect image will be formed. Oh, I'm extremely sorry, I made a mistake. It's not a small, but it's a magnified image. If I see if I see this ray diagram here, when it is between the focus and the pole, then one ray of light normally hits and is coming back to the center of curvature. The other ray of light hits at a certain angle and is reflected at the same angle, and they meet at this point. So it's a magnified image. So your small cheek hairs will appear big, and therefore it will find utility as a shaving mirror. So you've understood how a convex mirror can be used as a rear view mirror in car, how a concave mirror can be used when the source of light, whether bulb or LED, is at the focus. It can be used as a torch, or it can also be used as a shaving mirror when used close to the object. So many applications. Now let me go into a very important aspect, and that is multiple mirrors. See, the object of that we are considering will form an image. All right, now if you keep another mirror or another lens, that image will act as the object for the next step. Let me illustrate very clearly. Suppose you have, once again, you have a plane mirror. Oh, sorry. Suppose you have a plane mirror like this. Fair enough. Wait a second, let me draw it somewhere, say here. Yeah. Suppose you have a plane mirror like this. Fair enough. It is silvered out here. And this is the principal axis. All right. Fair enough. Now, you have an object like this. Of course, the first ray will hit like this, and the second ray will hit anywhere else like this. This ray of light will get reflected back, and this ray of light will get reflected in this way. And you know that a virtual and erect image will be formed here. So let me call this object as O, and let me call this image as I1. All right. Now consider I keep another huge concave mirror, and I know that a concave mirror is a converging mirror. So because this ray of light is coming here and this ray of light which is coming here, they are divergent rays of light. I want that I can somehow converge them using this concave mirror. So when this ray of light hits here, it's a parallel ray of light. It will run through the focus. So let me consider that the focus of this concave mirror is, say, at this point. All right. So as soon as a parallel ray of light will hit, it will meet the focus and move away in this manner. All right. And what about this ray of light? This ray of light will hit here, and let me assume that this is 90 degrees. All right. Let me for the time being assume that. And if that happens, then it will get reflected back in the same manner. So if it gets reflected back in the same manner, this is the ray of light here, and this is the ray of light here. Ideally, both of these rays would have gone and would have met here, and that is understandable because we know that a concave mirror will form a real erect image which is magnified, and that's what it would form. Let me call this image as I2. But notice that this piece of mirror is coming in between. So this ray of light, this white ray of light, and this white ray of light would actually hit this and get reflected back. All right, this will also hit this and it will get reflected back, and probably after getting reflected back, both of them will meet at a certain point, say here. Let this point be, say, I3. Actually, there's a high possibility that this I3 point is behind this mirror, and therefore there will be another reflection. But for the sake of convenience, I'm making I3 here. And then if you do a little bit of geometry, you'll find that this distance x and this distance y are equal. So just try to understand, this was our original object. This object created an image, a virtual image I1. This virtual image I1 served as the object for this concave mirror, because these were the incident rays of light. These white rays of light, these blue rays of light were the incident rays of light for this concave mirror. All right, and they appear to be coming from I1. So I1 is the object for this concave mirror. All right, and then we find that a certain object, that a certain image I2 would have been formed. This virtual image I2 serves as the object for this reflection process from the plane mirror the second time, and the image I3 which is formed is actually formed from the object I2. So the O goes to I1, I1 becomes a new object, it forms I2, I2 becomes a new object, and finally we get I3. And notice that because this is a plane mirror, this I2 and I3 must be equidistant from each other, of equal height, and serving all the concepts of plane mirror. So these concepts are so very important, and I'm just trying to give you an intuitive understanding. If you really want to draw the ray diagrams, you can draw, and I usually prefer to draw the ray diagrams because I know that at this and this distance, this is more or less the trend. All right, so now I'm going to talk about an important formula called the mirror formula, and that is 1 by V plus 1 by U equals 1 by F. Now, if you have either a convex mirror or you have a concave mirror, whatever you have, if you take this part, I'll consider this as the minus x-axis, this is the plus x-axis. Similarly, I'll consider this as the minus x-axis, the plus x-axis, just like a normal coordinate graph. So if any object is lying on this side of the mirror in the minus x-axis, I'll consider that object distance to be negative. And if any image is formed, say here, then this image distance will be negative. So if this distance is 25 centimeters, I will consider V as minus 25. Alright, I hope I have given that clear understanding. Similarly for a concave mirror. But if I am told that the convex mirror has a focal length of say 20 centimeter, I will consider F equal to 20 centimeter. In the case of concave mirror, if the focal length is 20 centimeter, for the purpose of this formula, I will consider F to be minus 20 centimeter. So I know when to take V as minus, U as minus, and when to take this F as minus. If you solve certain numerical problems, you'll understand it yourself. But just remember this convention of focal length, because if you do some mistake, if you get confused in this notation, then given a certain value of U, you'll get a wrong value of V. So I always prefer to draw the ray diagrams like this. For example, if I know that the V will be a huge distance away from the mirror, then I cross-check it with this formula. And if the formula gives me a small value of V, then I'm suspicious that I've been confused with the signs. So I first draw the ray diagram, get a mental picture as to where the image will most probably lie, what is more or less the distance from the mirror, and then I go with applying the formula. And one more thing that I'd like to say is that if you have, this is the image, right? This is the image, whereas this was the object, green one. So if the height of this object is say h1 and the height of this image is say h2, then h1 over h2 is the absolute value of the object distance upon the absolute value of the image distance. In other words, in general, no matter in the positive side or the negative side, or real image or virtual image or whatever, in general, if the object is farther away from the mirror, the height of the object will be relatively larger. Similarly, if the image is farther away from the mirror, the height of the image will be larger. So in these magnification cases, you find a lot of numericals coming in that fashion. And do refer to these ray diagrams and always understand the trend. In the case of convex mirror, you have only two trends. One, that the rays appear to be coming out of the focus here, and in this case, that the rays appear to be coming out from a point between the focus and the pole. In the case of concave mirrors, you have all of these variations. So do check them out, and I'll meet you with probably some more concepts, and finally going into refraction using lenses. And using lenses, the refraction has a similar formula. It's actually 1 by V minus 1 by U equal to 1 by F, but I won't confuse it right now with this formula. That's for a next video. So until next time, Do subscribe to News and Statics, share this video, like, stay updated, keep learning. Thank you.